All right, well, thank you everybody for the wonderful conference so far. I'm really happy to see so many people still here on Friday. So I want to talk about Earth's history, which is a theme that we've heard a couple of times during this meeting, and how when we think about Earth over its full geological history, in some ways Earth is more than one planet. And I want to give credit to Vicki Meadows for the title of this talk, because she was the first person who I think said these words to me. There's probably no better image that captures the idea of Earth as an exoplanet than the famous pale blue dot that was immortalized by Carl Sagan. So here's Earth suspended in a sunbeam, and this image was taken by Voyager 1 when it was about 6 billion kilometers away from our home planet, and it turned over its shoulder and it took this snapshot of our own planet. And this image is really important, not just because it captures the fragility of our own world, but also because in the context of exoplanets, these are what our first images of Earth-like exoplanets and of exoplanets in general are going to look like. So how can we learn information from these pale blue dots? Well, they have spectra. And so by studying and modeling the spectra of these worlds, these pale blue dots, we can begin to understand what we can and cannot observe from similar exoplanets. But while the planet that we live on is the best example of a habitable world, and it is, Earth is a planet, it is the planet we have the most data for, we don't yet know what the characteristics of other exoplanets are, whether they're Earth-like or Venus-like or Mars-like or Europa-like or anything like. So right now, the best we can do is try to understand what we might see from our own solar system. And so that's the idea I want to explore in this talk. I want to talk about Earth's history, and I want to talk about briefly some examples of alien phases of Earth's history and what we might be able to learn from them when thinking about the exoplanet population. What you're looking at on this slide is a timeline of Earth's history. So the timeline is on the left side of the slide, showing the age of the Earth on the y-axis billions of years ago, and then the x-axis of that sort of subway map plot on the left is the abundance of different gases in our atmosphere. And you can just sort of get a flavor for how these gases have evolved in our atmosphere over geological time. Now, on the right side of this figure shows different representative spectra that might be what our planet would have looked like to alien observers during these different phases of Earth's history. And I think it's really important to point out and really interesting to point out the fact that modern Earth spectrum may only be representative of about 13% of our planet's total inhabited history. So even though modern Earth is the best planet we have data for, it's maybe a weird phase of Earth's history when you look at the full span of geological time. And so it's useful and I think important to think about these earlier phases. So let's go through just a couple examples because I don't have time to go into any amount of detail on any one specific example, but let's just think about some of the implications of this for Earth's history. Okay, so let's consider one specific example in particular, and that's oxygen. Oxygen is an important gas when thinking about Earth-like exoplanets because oxygen is arguably the most important biosignature of Earth. It's the gas that when people talk about, looking for Earth-like exoplanets, what do we want to design a mission to look for? Well, we need that mission to look for oxygen, or at the very least, its photochemical byproduct, ozone. And so every conversation about, exoplanet observing missions always involves oxygen or its photochemical byproduct, ozone. But if you look at this plot from Chris Reinhardt's paper, this is showing how oxygen has not always been present in our planetary atmosphere. The history of oxygen is highly variable when you look over the full span of geological time. And I want to spend a lot of time talking about the Archean eon. The Archean is the earliest eon where we have a robust geological record. We have basically no geological record for the Hadean except maybe some zircons that have survived. But in the Archean, which is between about 4 and 2.5 billion years ago, we have geochemical evidence showing us that O2 was virtually absent from our planet's atmosphere. Okay, so what does that mean in the context of exoplanets, in the context of trying to detect life on exoplanets? Well, there was no detectable O2 in the Archean, but we do think there was abundant methane. Methane producing metabolisms, we think evolved at least by about 3.5 billion years ago, potentially earlier. And methane's photochemical lifetime in the anoxic Archean atmosphere would have been much longer than it was for the present day atmosphere. So you could build up a lot of methane, even at similar or even lower source fluxes compared to modern day Earth, just because it lasts so long in that anoxic context. Now, most of the methane that we're currently breathing in, there's about 1 part per million of methane that we're breathing in right now, is from a biological process called methanogenesis. Methanogenesis is a very simple, thought to have evolved very early kind of metabolism that takes CO2 and hydrogen and it makes methane and water. Biological production of methane on Earth outweighs abiotic production at a ratio of about 60-to-1. You've heard the word serpentinization before at this conference. So serpentinization is the dominant abiotic source of methane on our planet. What serpentinization is it's the hydration of certain iron and magnesium-rich rocks, like olivine and pyroxene. When you hydrate these rocks at, say, the Lost City hydrothermal vent system that you're looking at a picture of here, you can create a green mineral called serpentine. And this is also an exothermic reaction. It generates heat, and one of the byproducts is methane. So this is where most of Earth's abiotic methane comes from. Now, every time I talk about methane, in the context of biosignatures especially, I always like to talk about Titan as a counterpoint, right? Because Earth, modern Earth, and Archean Earth, methane is biosignature in that context. Methane, at least a large fraction of it, is produced by biology. Titan has an atmosphere that's a couple of percent methane. So how would we distinguish a planet, like Titan, where the methane is abiotic, from a planet like Archean Earth or modern Earth, where the methane is biological? Well, let's focus on serpentinization in particular, because that's something that people have done work on. So this is a great paper from Josh Chrysanthus and Totten. So this plot is from his paper. And what he did to create this figure that you're looking at here, this is the probability density of different methane fluxes. That's that blue curve you see to the left of that figure being produced by serpentinization, this non-life process. So he had a serpentinization model where he had different knobs in the model where he could turn different parameters that affect serpentinization, like the seafloor spreading rate, the fraction of the seafloor composed of the minerals that participate in serpentinization, et cetera, et cetera. And when he varies those knobs over ranges that he considered reasonable or plausible for a planet, a realistic planet, he gets this probability curve here. So the important thing to look at here is the fact that that blue curve is less than those lines you see on the right. So those are the modern biological methane flux as well as the estimated range of the Archean methane flux. You can see that they are higher, possibly higher than one might be able to plausibly explain from serpentinization. Now, there's still work to be done in this area, and there are other abiotic sources of methane. But the important takeaway here is that if you could infer a rapid production rate of methane that seems implausibly explained by abiotic processes, that may leave life as the most likely explanation. Okay, so now going back to Titan. Titan has a lot of methane, yes, but the methane in this extremely reducing atmosphere has an extremely long photochemical lifetime, at least relative to Earth, and that methane does not need a rapid production rate in order to sustain that methane at the concentration we see it in this photochemical context. So in this context, and all biosignatures are context dependent, the methane does not need life to explain it. Now for Earth, and for Archean Earth and modern Earth, it's a much more oxidizing atmosphere. Even for what I call the quote-unquote anoxic Archean, that's still a much more oxidizing atmosphere than Titan. There was still CO2 in that atmosphere, probably quite a lot of it. You have possibly less methane than Titan has, but it needs a much more rapid production rate in order to sustain that methane in that context. So all these things are context dependent. Titan has a haze. That is the most obvious first-order property of Titan. It's orange, it's hazy. It's the first thing anybody ever noticed about Titan. And believe it or not, going back to this timeline of Earth's history, there's geological evidence suggesting that the late Archean may have intermittently been hazy. So towards the late Archean, around about 2.7 billion years ago, there may have been a haze that occasionally appeared and disappeared in our planet's atmosphere when our planet had enough methane in it. And I think this period of Earth history is really important and interesting to think about in the context of exoplanets, because when we think about exoplanets, Like, we think about pale blue dots, right? But Archean Earth, if it had a haze, would have been a pale orange dot. So it challenges our notion of what an Earth-like planet might look like, because this planet looks alien, but if Earth really looked like this is by definition an Earth-like world. All right, so I've done some modeling work trying to understand what the implications of this haze would have been for Archean Earth. Unsurprisingly, the haze cools the surface of the planet. In my models, it cooled the surface by 20 to 30 degrees Kelvin, but you could still maintain habitability in the presence of other greenhouse gases consistent with geochemical constraints. Also relevant and important to habitability is this haze is a UV shield. So this haze would have existed in our Archean Earth atmosphere prior to the rise of oxygen and ozone. Now, ozone is important because ozone and oxygen are important because they shield the Earth from extremely damaging amounts of UV radiation. And in particular, UVC radiation, which is the shortest wavelengths of UV that can reach the planet's surface, those are really bad because they can directly disassociate bonds in our DNA. So this haze could potentially, in my models, blocked about 97% of the total UVC radiation from reaching the surface. And that sounds really good. Like, that sounds like a lot of blocking UV, like 97, that's great. But it's still way orders of magnitude more UVC than reached the surface compared to modern Earth. But it is low enough that certain radiation-tolerant organisms that even exist today might be able to survive under those conditions. So you don't need a UV shield to get life in the Archean. You can take refuge under other kinds of physical and chemical UV shields, like the water column, for example. But this might be one way to enable habitability at the surface of a planet, where, you know, on an exoplanet, you might be able to look for surface biosignatures if you can allow surface life. All right, so what does this do to the planet's spectrum if we're thinking about early Earth and hazy early Earth as an exoplanet? Well, here are three spectra showing three different haze thicknesses. The black spectrum is an Archean Earth planet with no haze. The blue spectrum is what I call a thin haze planet, and then the orange spectrum is what I call a thick haze planet. And the most obvious thing to notice is this huge absorption feature at short wavelengths. That blue UV absorption feature is the reason why Titan is orange, because it's absorbing blue light, and it's the reason why these hazes are a good UV shield. So this is a potentially, a spectral feature we might be able to go after on exoplanets. This feature is also a non-gaseous biosignature in the context of Earth, because the methane that produced that haze was produced by life. Okay, so going back to this timeline of Earth's history, I just want to talk briefly about the mid-Proterozoic, where we have another interesting situation going on. So in the mid-Proterozoic, there's evidence from Noah Polinovsky's work suggesting that O2 levels during this period may have been low, possibly as low as 0.1% of the present-day level. And that's important if that's the case, because that's too low to allow oxygen itself to be remotely observable. So yes, there was oxygen there, it was in the atmosphere, but you can't actually see that oxygen from the planet's spectrum with, any kind of reasonable telescope that we can imagine flying or having on the ground. But the important thing is ozone is the savior here, because oxygen has this wonderful photochemical byproduct, ozone, and ozone produces this whopping, huge, strong absorption feature at UV wavelengths, even at trace abundances. So even though we have very little O2 in the Proterozoic atmosphere, ozone is still detectable, potentially. And so here's a plot I really like from Stephanie Olson's work. So this is showing the UV spectrum. So from 0.15 to 0.35, those are all UV wavelengths of, potentially different flavors of Earth. The black spectrum there is a planet with no oxygen. That's a totally anoxic planet, no ozone, no oxygen. The purple spectrum is modern Earth. So you can see that produces this huge absorption feature. That's the ozone feature. What I think is interesting is that the blue, yellow, and red spectra, so those are for different amounts of ozone. And in particular, what Stephanie is showing in this paper is potential seasonal variability in the ozone abundance that would be driven by biology. And so this would be a temporal biosignature you might be able to go after. And you can only go after it for low oxygen planets. The reason is because if you look at the modern Earth spectrum, it's saturated. It basically reaches effectively zero flux at the bottom of that band. So if you're trying to look for subtle modulations in the strength of that absorption feature for modern Earth, you're not going to see them they're lost in the noise, right? You're getting no signal at the bottom of that band. But for Proterozoic Earth, where you're not saturated, you could potentially see these modulations. And so I think this is a really interesting temporal biosignature. Probably can't go after for modern Earth, it'd be too small to see, but maybe the detectability of this is enhanced for Proterozoic Earth, even though, counterintuitively it has less oxygen, but this other kind of temporal signature might be more detectable. All right, so I just want to wrap up by bringing us back to the pale blue dot and reminding us that not all exoplanets are going to look like pale blue dots. There might be pale orange dots or pale green dots or pale purple dots or whatever. So when we're anticipating what kinds of exoplanets we're looking for, Earth-like and otherwise, it's great to start in our solar system. And it's also really important to think about our solar system through time and, other kinds of planets that might exist in our imaginations that are physically possible. So modeling and theory and observations all need to come together to help us understand what we might look for. Thanks.